Well, good morning. I'd like to begin by thanking František and Bratislav for putting together the educational the workshop. I'm specifically going to focus on rewiring algorithms for connectomes and network neuroscience more generally. This is a topic that I'm particularly interested in, so I'm really happy to be able to present here and hopefully convey some of the advances in the field as well as the basic concepts. So, let me see. Can't seem to advance. There we go. So I'm going to begin with an example. Actually, I'm going to motivate most of my contact relative to the Drosophila connectome. And so this was a connectome that was recently mapped. It's a huge connectome, millions of connections, and roughly 128,000 nodes. The nodes in this connectome correspond to neurons. And so some recent work by Lin and colleagues performed a network analysis on the Drosophila connectome, and I'm going to focus on the global clustering coefficient. So they found that the clustering coefficient was 0.046, and so similar to the question that František posed. It's interesting to ask, what is this value typical for a connectome, or would it be considered large or small? You know, the value of 0.046 in and of itself is probably not particularly meaningful, and null models provide us with an answer to that question. So they give us a benchmark to which we can compare the value of the network measure, in this case the clustering coefficient, to that of a randomized network. By the way, for those of you that are not familiar with the clustering coefficient, as I've shown there in the top right, it's a very basic measure. If we have an apex node that's connected to two other nodes, it's simply the probability that we find a connection between those two other nodes. Okay, so going back to null modeling, the simplest kind of null model is a random network, otherwise known as an Erdos-Renyi graph. And this is really just a random network that has the same number of nodes and the same number of connections as our actual connectome. And we can compute the clustering coefficient in that random network and compare it to our actual connectome. So Lin and colleagues actually did this for Drosophila, and they found that in an ER graph, in a random graph, the average clustering coefficient is 0.0003. So there's actually a formula. When we're dealing with random graphs for basic network measures, we've got closed form formula, so we can just plug in the number of nodes, plug in the number of connections, and it will tell us the value of the clustering coefficient for that random network. So what they found is actually the clustering coefficient in Drosophila is 145 times higher than a random graph. So the conclusion here is that Drosophila is a highly clustered connectome. But as I'll show in a moment, the story is a little more complex than that when we start to dig into more stringent nulls. But before doing that, I just want to define very quickly what I mean by a random graph or an Erdos-Renyi graph. So as I've said already, it means that we're matching the number of nodes, the number of edges to our real connectome, and we also define a connection density P. And to build an Erdos-Renyi graph, it's really simple. We just go through each pair of nodes, and with a certain probability P, we draw an edge between those pair of nodes, otherwise not. And I've given some examples there of a graph, of random graphs on the right. So we're only matching the number of nodes and the number of edges, nothing else. The advantage of using an ER graph as a null is that we have, as I've already said, we've got closed form formula to determine the expected network, the value of our expected network measure. So we simply take the number of nodes, the number of edges, plug it into our formula, as I've shown there, and it will give us the value, our benchmark. And we can take that benchmark value and compare it to the value that we actually have in our empirical connectome. So it makes null modeling very easy. We take our formula, plug in the right value, and that's it. Some basic terminology before I move ahead. I've already defined what the clustering coefficient is. Going forward, I'm going to define the concept of node degree This is just the number of connections that come out or that are associated with a node. For a weighted graph, so in a graph where we have a weight associated with each connection, that could be, for example, a number of synapses in the case of Drosophila, we have the equivalent concept of node strength. And this is simply the sum of those weights across the connections associated with the node. And these are two important concepts that we'll need when we dive into rewiring algorithms. So as František already raised the concept of a strawman null, if we, using the ER graph or random networks in the field is often considered a weak benchmark. So other than the number of nodes and the number of edges, ER graphs don't preserve basic connectome properties, such as the node degree, for example. So the consequence of that is that if we find that, for example, the Drosophila is 145 times more clustered than a random graph, it might be that this huge difference in clustering is trivially or simply due to some other measure that we haven't matched in our null network. So it might be, for example, the node degree, the fact that the node degree in our null network could be vastly different to what it is in our observed connectome. It might be that which is driving this huge difference in the clustering coefficient, not the clustering of the network itself. Remember, as František said, that these network measures are interrelated. So this suggests that we might need to consider a more stringent null. And to do that, we can use a rewiring algorithm. The basic strategy of a rewiring algorithm is we take our original connectome, we shuffle edges in a particular way, that generates a sample rewired graph, and then we compute our measure of interest in the rewired graph to build up a null distribution. And we repeat that for multiple rewirings. And so each rewiring of the connectome gives us one sample from that null distribution that František put up and for which he computed a p-value. So Lin and colleagues actually did this. They used a rewiring algorithm, I'll go into the details of that in a moment, on the Drosophila connectome, and what they found is that when they rewire and they preserve the node degree, the actual clustering coefficient in Drosophila was only 7.6 times higher than their null, than their rewired graph. And so this suggests that actually node degree was contributing to that huge discrepancy when they looked at the more simple null, the strawman null, based on an ER graph. So how do we actually rewire? How do we generate these samples that I've shown there on the left? How do we rewire a graph? The classic rewiring algorithm is referred to as Maslov-Sneppen rewiring, and this was proposed, well, more than 20 years ago now. It was used to rewire protein-protein interaction networks. But this has become a very widespread algorithm, and it's a very easy algorithm to understand. We start with our original connectome. We select 4 nodes at random that I've denoted there, U, V, and IJ. And if there are 2 connections between those 4 nodes, we simply switch those connections such that rather than U and V being connected with each other, we have U and I, and rather I and J, we have V and J. And that's considered one swap. Once we've done that, we go back and do the same thing again. We choose another 4 nodes. If they're connected, we rewire them as such. And so each time we perform we look at those 4 nodes and rewire them, we gradually randomize our network. And so once we've chosen a sufficient number of these swaps, we end up randomizing our network, and that gives us one sample from that null distribution that František showed us. By the way, in my slides, I'm going to provide links or the actual function from the BCT, the Brain Connectivity Toolbox, to achieve the rewiring algorithms that I'll present. They'll be shown in purple. So in this case, it's the RAND MIO undirected to perform Maslov-Sneppen rewiring. Now, the original Maslov-Sneppen rewiring algorithm was only for binary and undirected graphs. But Rubinov and Micah and Ruben and Olaf proposed some extensions to the basic algorithm, the rewiring algorithm, that allows us to apply it to signed graphs. So that's when we got positive and negative edges, potentially inhibitory or excitatory, as well as weighted graphs. So rather than preserving the node degree, we can also preserve node strength. There are these extensions are heuristics, and sometimes they don't work. I won't go into the details there, but I'd be happy to discuss that with you after. Now, there are some minor problems with the Maslov-Sneppen rewiring algorithm. First of all, it does potentially, in some cases, introduce a mild sampling bias. So when we generate a random network, when we rewire, we want to make sure that we're sampling uniformly from the space of all possible random networks. But it turns out that with MS rewiring, it's more, or in some cases, it will sample certain instantiations or certain samples from the null more likely than others. And this is referred to as biased sampling. So our null distribution might not necessarily be the true null distribution. The other problem or limitation is that it's quite slow. So when we're dealing with connectomes like Drosophila that comprise millions of connections, it can take a long time to generate one sample or one randomization of our network. So there have been some advances and alternatives to MS to address these problems. And to understand those, we've got to get a sense of how these algorithms work. And these are modeled using a Markov chain. Don't worry if you don't know too much of the details of a Markov chain. I won't spend a lot of time on this. But the basic idea is that each rewiring step, so when we take those 4 nodes, it's often referred to as a checkerboard pattern, and we perform a rewiring, that's one step in a Markov chain. And each state in our Markov chain is the rewired network. So we can model the rewiring as a Markov chain. And what I've shown on the right there is a simple 3-node graph. And the fractions that I've shown are probabilities. That's the stationary distribution of the Markov chain. And you can see that the central rewiring has a higher probability. And so that means with the classic MS rewiring algorithm, we're more likely to sample that central network than the 4 networks that sit on the periphery. So to overcome that bias, a more recent approach is the switch and hold rewiring algorithm. And I won't go into the details of this, but the basic idea is that when we sample 4 nodes, if those 4 nodes can't be rewired, so if there are no connections between them, or if there's only one, or if there are more than 2, we keep sampling from the old network that we generated. And by doing this, we ensure that we achieve a uniform sampling of the null space. Then we come to some of the state-of-the-art. So taking a step back, the switch and hold algorithm that I just discussed, that works well. It overcomes the uniform bias, but it is still quite slow. It takes a lot of time to generate a sample. So the state-of-the-art in rewiring is the curveball and fastball algorithms. These are relatively new. They were proposed 5 or so years ago. They're more or less the same. Fastball has some algorithmic tweaks to speed things up. But these are really fast, and they also overcome the mild bias in Maslov-Sneppen algorithms. And the basic idea, I'm not going to go into the details, but you can think of these algorithms, they work, or they're analogous to how kids trade playing cards. So the idea is that each child represents a node in the network, and the connections associated with the node are the playing cards. And so what we do, each step of the algorithm, we select 2 children, 2 nodes in other words, we take their connections, put them in a pile, shuffle them, and then we take a card off the deck and assign it to one of the children, take the next one to the other one, and so on and so forth. And that achieves our network randomization. So rather than performing randomization across 4 nodes, choosing 4 nodes, we actually randomize across all of the connections associated with two nodes. So check those out. Those 2 algorithms are quite fast. So taking a step back, and this also follows on from what František mentioned, is where do we draw the line? You know, I've said that we should preserve, with these rewiring algorithms that I've presented thus far, we're preserving the number of nodes, the number of edges, as well as the node degree. So they're the 3 properties that we're preserving in our null network. And you might ask, why do we stop there? right? Why don't we go ahead and preserve other properties of the null? Why don't we go ahead and preserve, for example, the connection lengths? None of the algorithms that I've presented so far care about connection length. Or why don't we preserve other aspects of the geometry? Where do we draw the line? And so you'll find that most of the studies in the field draw the line here. So they'll use a rewiring algorithm that preserves degree, nodes and edges. More recently, however, there has been a focus on, as František has already alluded to, preserving connection length and other geometric aspects, because we know that these networks are spatially embedded. We can also view this as a nested family of nulls. So the outmost circle that I've shown here is the space of all possible random networks. And then we can constrain our null space by adding more and more features, more and more structure to the network. And once we add a sufficient structure, we're eventually going to converge on our actual observed connectome. So it's going to become harder and harder to beat our null. And I completely agree with what František said. There's no right or wrong point along here as to where we should say this is the ideal null for our particular application. But what would an ideal null look like? And in my opinion, the ideal null should preserve all the connectome properties, except for the property that we're aiming to benchmark. But the problem here is it's really hard to generate a network that knocks out one specific property but preserves the rest. And that's because all of our network properties are interrelated. So as soon as we try to randomize or destroy one property, it's inevitable that this then impacts other properties of the network. And Micah has some interesting, check the citation that I've given on the bottom. This has actually been used as a criticism of the field, given that all of these network measures are interrelated, that perhaps we're studying the same thing but under a different, in a different guise. So in the final part of the presentation, I'm just going to give an overview of some of the more advanced rewiring algorithms. And these algorithms begin to preserve geometric properties of the connectome. So with those classic rewiring algorithms that I've already presented, they don't take into account connection length. And what typically happens is that the rewired networks have much longer connection length, so the wiring cost is significantly higher than the true connectome that we're studying. So there have been various extensions of rewiring algorithms to preserve connection length. This is some work by Roberts and colleagues from quite a few years ago now, and the basic idea is that we model the relationship between connection strength, which is on the y-axis here, and connection distance. And once we do that, the idea is that we regress out this effect, and then we shuffle the residuals. So this induces the randomization in our network, and then we add back the effect of length. And this gives us a sample from our null. Now this in and of itself doesn't necessarily preserve the node strength or the node degree. It's just a random shuffling of the residuals, but there are a few post-processing steps that the authors propose to then bring back the correct node degree in the randomized network. And so what they show here is that once they bring back the strength, you can see that the hubs of the network are proposed. So the top image there is the actual connectome, and the one on the bottom right is the randomized version. And you can see that the actual hubs of the network, the highly connected nodes, are preserved in our null. So going back to Drosophila, what we can then do is we can apply each of these different or these more stringent nulls to our Drosophila connectome and see how that affects our interpretation or our benchmarking of the clustering coefficient. So remember, the actual clustering coefficient was 0.046. We considered our most basic null, where we only preserve nodes and edges, and we saw that the clustering coefficient was way extraordinarily more higher than that strawman null. We then used the rewiring algorithm to preserve node degrees, and we see then it was only 7.6 times higher than our null. And then we went to our more fancy length-preserving null, so we actually preserved the distance, the physical length of our connections. And in that case, it was only 1.4 times higher. So this really illustrates the point that František got to. As we add more and more structure to our null, it becomes harder and harder to reject the null hypothesis. And I think this is a good way to go, because this really tells us, if we look at this nested family of nulls, it really tells us how or what properties are having the strongest effect on our measure of interest. Another important benefit of using nulls is that they allow us to compare measures across species. This is a busy slide, but what the authors are doing here is comparing their network measures in the Drosophila to other species, C. elegans and zebrafish. And if you focus on the last row there, where we're looking at the clustering coefficient, they've shown how much more the clustering coefficient is greater than a random graph, or CFG is basically a different type of null model that also preserves no degree. And while we can't compare raw network measures across species, because these don't take into account differences in the size of the networks, it makes sense to compare the benchmark measures, or actually how much the measure is. So we can compare that, for example, the fly, the Drosophila, is 144 times more clustered than 144 versus 4.06 in C. elegans. So it makes sense to compare across species. Just very quickly to wrap things up, another approach is partial rewiring. So the idea here is that rather than completely randomizing the network, we only randomize certain regions or canonical networks, or we only randomize a fraction of the random of edges. And so some work by Golo looked at this in terms of the fragility of a hub. So how much do we have to randomize the network before a hub is no longer a hub? And so if a hub deteriorates quite quickly, we say that it's a fragile hub. In contrast, if we really need to randomize most of the network before that hub gets knocked out, that hub is considered a resilient hub. So to wrap up, I just want to very briefly consider when to use and when not to use network rewiring nulls. So if you have a functional network that you've mapped using resting state fMRI and a measure of functional connectivity such as correlation, a rewiring algorithm is probably not the right way to go. I mean, you can do it, but because of the structure that the correlation or functional measures induce on the network, rewiring won't preserve those structures. So in that case, we'd better off to use time series randomization, and we'll have a talk about that later on. If you're wanting to preserve high order properties of the network, such as modularity, for example, rewiring algorithms are also probably not the right way to go. They can't preserve high order properties, and so you'd be better off using a generative model, such as a stochastic block model or an ERGM type model. So that leaves us, when you should use a rewiring, or when a rewiring algorithm is most suited, is for a structural network, and when you're only wanting to preserve basic topological properties or perhaps some basic geometric properties of the network. That's when a rewiring algorithm is most suited for your purpose. So to summarize, null models set expectations for network organization under certain null hypotheses. They preserve the number of nodes, edges, and node degree. They're the basic topological properties that we preserve. I would recommend starting with Maslov-Sneppen rewiring. It works well for all types of connectomes, weighted, directed, binary, and signed. It does have a few limitations. It has a mild sampling bias, but I wouldn't worry about that too much. If you have a binary and undirected network, consider some of the more state-of-the-art rewiring, such as curveball and the switch and hold algorithm. They overcome the bias, and they're also super fast. So if you've got really large connectomes, this is probably your first option. And I also briefly touched on geometry preserving rewiring algorithms, and this is something that has grown in interest in the field. So some further reading, I can highly recommend the review by František and Bratislav that came up a couple of years ago. Chapter 10 of Fundamentals of Brain Network Analysis focuses on nulls. I also like it's quite an old paper, but very relevant on weighted randomization by Micah and Olaf. It's a neuroimage paper. So to wrap up, as I promised, this is the code if you're wanting to implement these rewiring algorithms in your own work. Maslov-Sneppen is available in BCT, both the Python and MATLAB versions. It's also in NetworkX. Curveball and Fastball are relatively new. There are implementations that are available. I haven't actually tried these myself, so I can't give you any further details, but it'd be interesting to give those a go. Length preserving rewiring, I've given a GitHub link, and František and Bratislav have also put together a nice compilation of various null models. So check out the GitHub link there on the bottom of the slide. So just to wrap up, I fully agree with František's early point. There's no right or wrong null model. I see this as an evolving field, and I sort of think about this as how the concept of a yardstick evolves over the years. So initially, the benchmark for a yardstick was the distance between the king's nose and his thumb. And then it's evolved to become a bronze bar, the length of a bronze bar that was stored in a repository, and then it eventually evolved to what we now know to a meter. So this is how I see the field of null modeling. It's really an evolving field, and there's no right or wrong null for your particular application. So I'll stop there. Happy to take questions and happy to chat with people after the course. Yeah. I probably wouldn't go as far as to say that it's inappropriate, but when you use, so functional networks would typically be mapped using, for example, a correlation coefficient or some other measure of statistical dependency, and that measure would be applied to a time series. And then when you use the correlation coefficient, that will introduce something called transitivity. So if you have two connections, you have a node that's connected to two other nodes, and you have a strong correlation between the two, it's more likely that you'll find a correlation between the other nodes. So there's an inherent structure that your measure of connectivity is inducing on your network. And what happens when you rewire an algorithm, it doesn't take that into account. So the rewired algorithm doesn't preserve the induced structure that's owing to your functional measure. So it could be argued that if you do use a rewire, and once again, I'm not saying that that's a wrong option, but if you do use that, your null might be perhaps too optimistic because of the structure that is induced from your measure of functional connectivity. I hope that addresses. Okay, yep.
Geometry preserving measures, and you mentioned path lengths or distance preserving. I was wondering how you would, just in the Strawman to Steelman spectrum, where you would put sort of like geometric graph analysis preservations, like if you want to preserve some or all of the Laplacian eigenvalues, for example, or other kinds of geometry. Like where would you put that sort of angle or something? Because that's definitely different from sort of Chaplin's local.
Yeah. Yeah, I guess even the way that I'll try not to spend too much time flicking through slides, but in this conceptualization here, the order, I mean, I've shown here that we have node edges and degree, and then I've added connection length. This is just a timeline of how nulls have evolved in the field, but there's no reason why in another world where it might have actually been that geometry has come first, and then we've gone on and preserved node degree. So there's no fundamental reason why, it's just the way that this has evolved in our field. I think you mentioned where would geometry be placed here. Once again, in the way that things have evolved in network neuroscience, is probably a more recent inclusion. It's a more recent property that we've considered. But there's no as I said, there's no theoretical reason of how these are ordered or what's a more, how do you define what's a more complex measure versus a more basic measure is something that can be debated.
Absolutely, and sorry, I guess I should be slightly more clear, but when we talk about sort of like choosing local versus global properties to fix versus shuffle,
Yeah.
what utility do you see for sort of geometric in a global sense, or in maybe like sort of a differential geometric sense? Where do you see those tools having either advantages or disadvantages against sort of more traditional graph theory summary type measures?
Look, I think it really depends on what you're wanting to test. If your question is really about geometry, you're wanting to understand how geometry affects or impacts your measure, then of course building geometric aspects and taking into account the spatial embedding of your network is critical, right? But if perhaps the question that you're asking, your application doesn't have a geometric focus, then building that into your null might not be as important. My recommendation would be to consider a family of nulls and building in further and further or greater and greater structural properties into that until you can't reject or you can't, Happy to chat with you after if you... Maybe one more question, I don't want to take up time of the other speakers. Yeah. Yeah, so lattice null models are important for small worldness. So for those of you that know, lattice is basically where you arrange, or the simplest way to laticize is arrange connections in a grid, and you only connect to your neighbors. And there are also algorithms to laticize a connectome, which is also could be considered a type of rewiring as well. So the typical application of those would be when you're wanting to test whether your network, or in terms of understanding small worldness, at one end you have a lattice network, at the other end you have a random network. So the lattice has very small connection lengths, a random network has quite long, and so these are one of the applications of lattice networks. I guess in current applications, latticization is probably not as prevalent now. I think it's not commonly used, but certainly if you're interested, there are functions in BCT that would enable you to laticize as well as generate lattice networks. I think I'll stop there. I don't want to take up time for the other speakers. That's okay. All right. Well, is there any other questions? Otherwise, happy to. Yeah. Yeah, it's an interesting game. Most of the work in the field is a global test, so you'll have an empirical null that you generate, which would represent the network as a whole, and so then you would test the null hypothesis across the network as a whole. But there has been some work, so that work that I showed with by Golo that focused on partial randomization. So the idea is there, rather than having a global test, you're actually testing where you potentially randomize within a certain locale of the network, perhaps a certain canonical network, the default mode, or an executive network, and only randomize that part and understand its effect on the network. But yeah, it's still an open field, and there's not as far as I know, not a lot of work that's focused on partial randomization or randomizing only certain parts of the network. I think that would then lead into the question or the concern that you raised regarding multiple comparisons and the issues associated with that, because then potentially you've got multiple tests that you're considering or hypotheses that you're testing across the different parts of the network. But there might be a fruitful area to investigate. Okay, thanks again, and I think we can move on to Rick Betzel, who will introduce generative models for null modeling.